I'm Takumi Aoki from Hosei University. We will introduce our research, text classification through Glyph-aware Disentangled character embedding, and semantic subcharacter augmentation. Glyph-aware character embedding has a number of attractive advantages, and today's talk is a proposal of the method that increases the interpretability of the embedding and performance of the model on them. The proposed Glyph-aware Disentangled character embedding enhances the interpretability, and the proposed semantic subcharacter augmentation improves the performance. First, we introduce Glyph-aware NLP. We define Glyph-aware NLP as an extension of image-based character embedding. Some Asian languages such as Japanese and Chinese use glyph to give visual meaning to characters. Here we call glyph as the shape of the characters, especially as illustrated subcharacter often indicates the common meaning. In this example, rope and cord have the same subcharacter meaning thread. We believe that proper handling of the subcharacter can improve the interpretability and performance of the NLP model. The Glyph-aware NLP has several meaningful advantages in handling Japanese, Chinese, and some other languages. For instance, no need word segmentation, effectively utilizing character shape, and applicable image-based data augmentation. In particular, no need word segmentation is effective in Asian languages because there is no clear separate between words, and it is difficult to segment words. Second, I will introduce effective data augmentation for image-based character embedding in the next slide. Data augmentation is essential in deep learning in terms of ensuring the robustness of the model. In general, in NLP, it is difficult to apply data augmentation because of the need to consider the context. By using image-based character embedding, we can apply a variety of data augmentation methods that do not require the contextual analysis used in computer vision. In sum, image-based character embedding is very effective for processing the Asian languages. However, there is room for improvement in the interpretability of the embedding and robustness of the model. So, we propose Glyph-aware Disentangled character embedding, GDC, and semantic subcharacter augmentation, SSA. The proposed GDC provides a disentangled character embedding in which each of the dimensions corresponds to the structure of the subcharacter. The SSA replaces the subcharacter of a character with another readable subcharacter. Next, I introduce the details of our framework. The slide proposes an overview of our framework. Each character in the target text is transformed into an image and forwarded to the subsequent validation character encoder, VCE. The VCE is basically composed of a beta VAE, and it obtains the proposed GDC. Owing to the attractive property of the GDC, character level text classifiers such as CLCN can take advantage of the interpretable and highly effective data augmentation method SSA. Next, I introduce the detail of the GDC. In order to achieve GDC, we use beta VAE as a validation character encoder. The beta VAE provides a high independent embedding where each dimension follows a nearly normal distribution. Based on these desirable features, we expect each of the important subcharacter structures to be embedded in certain dimensions. Next, I introduce the detail of another proposal, SSA. The SSA adds perturbation to only one dimension of the embedding. Taking advantage of the preferred features of the embedding created by our GDC, we expect that the subcharacter will be replaced by another readable subcharacter. To evaluate our framework, we perform two text classification tasks. The first one is for class document level classification task with 22,000 data. In training, 128 characters were extracted from the text. For evaluation, 128 characters were slide one by one. The entire text was used as the input. The other is 9 class sentence level classification task with around 7,000 data. In training and evaluation, 80 characters were extracted from the text. The variation character encoder is pre-trained with Japanese characters. Here is a summary of the classification performance. We can confirm the proposal framework GDC SSA shows the highest performance among our evaluation. In the GDC, the SSA is better performance than the WT, convention dropout-based data augmentation method. While on the other hand, in the CA, the WT is better performance than the SSA. In this next slide, I show the effectiveness of the proposal on interpretation and why the WT is better than the SSA for the conventional CA. The slide compares the reconstructed character when punctuation is added on only one dimension of the embedding. In the GDC, on the left, the punctuation gives the subcharacter a meaningful change. In this example, road of subcharacter change road or water. Thread of subcharacter change hand or gold. This may be due to the fact that the GDC had a standardized metric in the embedding space and they are dimensionally independent. Thus, each dimension of embedding by the GDC could store the subcharacter. On the other hand, the conventional CA did not provide such a desirable replacement. This may be the reason why the application of the SSA did not improve the accuracy in the CA compared to the WT. Finally, I conclude my presentation. The GDC improved the interpretability of the character embedding, and the SSA improved the model performance. This helped to improve the interpretability and robustness of our proposed framework. That's all. Thank you for listening.